So next, let's look at how to distinguish between linear and nonlinear relations. So in chapter 3, we talk about the linear functions graph is a straight line, right? But in the real data, real world data, and we cannot continuously collect the data set. Therefore, all the data we are going to see will be the scattered data, not the continuous data. And in the real life data, nothing will fit perfectly in a straight line. Therefore, in a scattered data diagram, you will see a data band instead of the data falls on the straight line. So like this, you will see a band of data, and each point still represent a order pair of the data set, So when we say in the scattered data diagram, if the data band forms approximately a straight line band, we call it data is linear, So for the this graph, we say the data is a linear data, because band is kind of forms a straight line, and this is the slope positive linear data. And the second one, B, we also say this is a linear data, this scattered datagram, because the data band is kind of, form a straight line band, and this linear data have negative slope because going downward. And the C, if we, kind of graph in the middle, you will see the curve. This is more like a quadratic data, it's like a parabola, right? The data band more like a parabola, and then parabola open down. So this data is nonlinear. And then with the tails, with the curves, this one obviously is not, a line, right? It's a curve. So this is nonlinear data. And this one also have a curve, right? Nonlinear data, this is more like an exponential data graph, right? The scattered data diagram is more like a exponential data. All right, so let's try some examples. So determine whether the relationship between two variables in each scatter diagram in this figure is linear or nonlinear. So we can see this data band is formed the lines, right, basically. So this is linear data. This data band, more like a open upward parabola. So this is a nonlinear. This one with the curve, so nonlinear. And this one have a curve, nonlinear. More like exponential data. So to distinguish linear data from nonlinear is pretty straightforward. If data band forms a line, and then we call the data is linear. So linear could be linear going up, right? The line trend is going uphill. When that is case, we say the slope is positive, or linear band goes downwards like this. So we say the slope of the linear function is going downwards, decreasing. So that's the answer for the previous example. And find a model for linearly related data. So from the previous example, in table 6, which is, I can show you real quick which one is in the last video. This data set, that's the table 6, right? The x-axis represent the on-base percentage, the y-axis represent the run scored. All right. So let's go back to our slides. So use that data, okay, select 2 points and find the equation of the line containing the points, and then graph the line on the scatter diagram, okay? So we're gonna do that. And then we're going to select these 2 points, okay, as the book, and then the slope of the line, okay, passing through these 2 points will be, if we denote, this is x1, y1, this is a x2, y2, and then the rise will be 688 subtract 610, right? This is a rise. And the run will be x2 minus x1, which is 32.1, subtract 30.6, okay? So if you use a calculator, rise is 78, run is 1.5, and then divide these 2 numbers, we got a slope equals 52. So now we know the slope, we know the line, we can use point slope form of line equation, okay, plug in. So we write a point slope form, standard form, y minus y1 equals m times x minus x1. So here, if we use the first point, this as x1, y1, and the slope equals 52, right? We already calculated earlier. So now we plug it in. Okay, x1, this put in here, y1, plug in here, slope 52, plug in here. So we got this linear function. Y minus 610 equals 52 times x minus x1, which is x minus 30.6. And then right-hand side distributive, right? Eliminate the parentheses. So we got a 52x minus, use the 52 times 30.6, we got a 5091.2. And then left-hand side, we still have a constant term, so we need to move to the right-hand side, combine with this constant, right? So both sides of the equation add a 610, and then finally we got a line equation. Y equals 52x minus 981.2. So that's the linear model we identified, okay, if we select the 2 points, okay, from the line. All right, so now let's look at the graph. Okay, previously we graphed the scatter data diagram, right? So if we connect these 2 points, use the straight line, okay, that's the line passing through, okay? So now the question is, we choose these 2 points to build up the linear function, okay, represent this model. What if somebody else choose these 2 points, and then it will get this kind of line? I'm sorry, this is not accurate. Okay, I'm sorry. Let me draw it again. So if somebody use these 2 points, okay, and then it formed the line like that. Okay, what if some other people use these 2 lines and then it will draw the line like that? So which linear function we should use, okay, to represent this data set? Okay, if we can randomly choose any 2 points to build up the linear function, and then everybody will come up with different one, who is the better one, right? Which linear function is better represent the data? So when this question arises, and then the solution will be, we're going to use the graphic calculator to help us to find the linear function best fit this data. Okay, so we're gonna use graphic calculator, find the line of best fit.